There is a tissue in your body that surrounds every muscle, every organ, every nerve, every blood vessel, and every bone. It wraps them individually, groups them into functional units, connects them to each other, and forms a continuous three-dimensional web that extends from the top of your skull to the soles of your feet without a single interruption. It makes up roughly 20% of your body's total volume. It transmits force across your entire body when any part of you moves. It contains more sensory nerve endings than any other tissue in the musculoskeletal system. And for most of the history of anatomy, it was thrown away. When anatomists dissected cadavers, the white, filmy, seemingly featureless tissue that surrounded the muscles and filled the spaces between structures was systematically removed and discarded so the interesting parts, the muscles, the bones, the organs, could be examined and studied. It was called packing material, anatomical stuffing, the biological equivalent of bubble wrap. It had a name, fascia, from the Latin word for band or bundle, but it had no respected function. It was categorized as connective tissue, which was the anatomical equivalent of miscellaneous. For centuries, the most abundant structural tissue in the human body was considered physiologically irrelevant. That assessment was catastrophically wrong, and the reversal of it, which began in earnest in 2007 with the first International Fascia Research Congress and has accelerated dramatically since, represents one of the most significant reframings in modern anatomy and movement science. What researchers discovered when they finally studied fascia with the tools of molecular biology, electron microscopy, and real-time imaging is that this tissue is not passive packaging. It is a dynamic, metabolically active, mechanosensitive organ that responds to mechanical load, remodels its structure in response to habitual movement patterns, generates and transmits force across the body in ways that muscle alone cannot account for, and contains a sensory apparatus so extensive that it may be one of the primary sources of chronic musculoskeletal pain in the human body. To understand what fascia actually is and why it matters, you need to start with its structure. Fascia is primarily composed of collagen, the most abundant protein in the human body. But not all collagen is the same, and the specific organization of collagen fibers within fascial tissue is what gives it its remarkable mechanical properties. Type 1 collagen, the predominant collagen in dense regular connective tissue like tendons and ligaments, consists of long, parallel fibers that provide extraordinary tensile strength in a single direction. Type 3 collagen, more abundant in loose connective tissue and in fascia that must accommodate multi-directional movement, forms a more loosely organized network. In fascial sheets like the thoracolumbar fascia covering the lower back, the plantar fascia covering the sole of the foot, and the deep fascia of the limbs, collagen fibers are organized in multiple layers, with each layer running at a different angle, creating a laminated structure that provides mechanical resistance in multiple directions simultaneously. The architecture is not random. It is precisely organized in response to the mechanical demands placed on each region of the body. Living within this collagen matrix are cells called fibroblasts. Fibroblasts are the primary cellular inhabitants of connective tissue, and their job is to synthesize and maintain the extracellular matrix of collagen and other structural proteins that surrounds them. But fibroblasts are not passive secretory cells running a fixed production program. They are mechanosensitive. They have surface receptors called integrins that span the cell membrane and physically connect the cytoskeleton of the cell to the collagen matrix outside it. When the collagen matrix is deformed by mechanical load, the integrins transmit that deformation into the cell interior, triggering changes in gene expression, protein synthesis, and cell behavior. The fibroblast literally feels the mechanical environment it inhabits and adjusts what it produces accordingly. This process, by which mechanical signals are converted into biological responses at the cellular level, is called mechanotransduction, and it is the mechanism by which fascia encodes mechanical history. When you repeatedly hold a particular position, when you sit for 8 hours a day with your shoulders rounded forward and your head pushed toward a screen, or when you stand for hours with your weight shifted to one leg, or when you perform a repetitive occupational movement thousands of times per day, the fascial tissue in the regions under chronic load experiences sustained mechanical deformation. The fibroblasts in those regions detect this deformation through their integrins and respond by increasing collagen synthesis in the direction of the habitual load. Over weeks and months, the collagen architecture of the fascia remodels to align with the direction of the chronic mechanical stress. New collagen fibers are deposited parallel to the direction of habitual tension. Crosslinks form between adjacent fibers, increasing stiffness in that direction. The water content of the ground substance, the hydrated gel that fills the spaces between collagen fibers, decreases in regions of chronic compression, reducing the fluid capacity that allows the tissue to deform and recover. The fascia literally grows into the shape of your most common positions. It remembers them not as a neural memory, not as a muscular habit, but as a structural reality encoded in the molecular architecture of the collagen matrix itself. This is the mechanism behind postural compensation. When a physical therapist looks at someone who has spent 20 years working at a desk and sees the rounded upper back, the forward head position, the protracted shoulders, they are looking at the external expression of a fascial adaptation. The muscles of the chest and anterior neck have not simply become tight in the way a muscle cramps. The fascia surrounding them has remodeled. The collagen architecture has reorganized to accommodate and then enforce the forward position. The tissue has become, at the structural level, shorter and denser in the anterior direction and longer and less organized in the posterior direction. Simply telling the person to sit up straight is asking them to work against a fascial architecture that has been physically redesigned by years of mechanical load to resist exactly that correction. The problem is not lack of effort or awareness. The problem is that the tissue itself has been remodeled. Now here is the dimension of this story that most people in pain have never been told. Fascia is exquisitely sensitive to pain. The fascial layers contain an extraordinary density of sensory nerve endings, including free nerve endings, that function as nociceptors, pain-detecting neurons that fire in response to mechanical deformation, chemical changes, and inflammatory mediators in the tissue. Research has shown that the deep fascia of the limbs and trunk contains up to 10 times more nociceptors per gram of tissue than the muscle it surrounds. The implication is significant. When you feel what you think is muscle pain, the burning in your lower back after a long day sitting, the ache in your neck after staring at a screen, the persistent tension in your hips after long drives, the pain is likely originating at least partly and sometimes primarily in the fascia, not the muscle itself. The muscle may be fine. The fascia surrounding it is compressed, inflamed, or mechanically distorted, and its dense sensory innervation is broadcasting that distortion as pain. Fascial pain has a characteristic quality that distinguishes it from pure muscle pain. It tends to be diffuse rather than precisely localized because the fascial network is continuous and a local restriction can create tension patterns that manifest as pain at a distance from the original site. It tends to be worse with sustained positions rather than with movement because sustained positions create sustained fascial deformation and sustained nociceptor activation. And it tends to be accompanied by a sense of stiffness, of the body being somehow stuck or restricted, that persists even after the acute pain has faded because the underlying fascial architecture that is creating the restriction has not changed. Understanding fascia as a sensory organ also reframes the mechanism of several manual therapy techniques whose effects have been difficult to explain through purely muscular models. Foam rolling, for example, does not break up fascial adhesions in the dramatic sense that the popular description implies. Fascia does not develop literal adhesions that are disrupted by pressure in the way a scar can be manually broken down. What foam rolling does is exploit a property of fascia called thixotropy. Thixotropy is the property of certain gels and semi-solid materials to become less viscous, more fluid, when they are agitated or subjected to mechanical stress, and to return to a more gel-like state when left at rest. The ground substance of fascia, the hydrated proteoglycan gel that fills the spaces between collagen fibers, is thixotropic. When you apply mechanical pressure to a fascial region through foam rolling or massage, the ground substance temporarily becomes more fluid, the collagen fibers can slide more freely relative to each other, and the tissue's mechanical stiffness transiently decreases. The sensation of release you feel after foam rolling is real, and it is explained by thixotropy, but the effect is temporary. As the mechanical agitation stops and the tissue returns to rest, the ground substance returns toward its baseline viscosity. This is why regular, repeated application is necessary for any sustained change in fascial mobility, and why a single foam rolling session, however thorough, does not produce lasting structural change. Lasting structural change in fascia requires a different type of intervention. It requires sustained mechanical loading over time, what physical therapists call prolonged stretching or sustained load. The reason is that collagen remodeling, the actual reorganization of the molecular architecture of the tissue, operates on a much slower timescale than the thixotropic response. Collagen synthesis takes days to weeks. Collagen degradation and reorganization takes weeks to months. For the fibroblasts in a region of fascia, to receive sufficient mechanotransductive signals to upregulate collagen synthesis in a new direction, to break down the existing crosslinks in the old direction, and to deposit new collagen aligned with the new mechanical environment, the mechanical load must be sustained for long enough and repeated frequently enough that the cells accumulate sufficient signal to alter their gene expression patterns and begin the remodeling process. Research suggests that holds of at least 90 seconds to several minutes are required to begin producing meaningful viscoelastic change in fascial tissue, and that consistent practice over weeks to months is required for structural remodeling to occur. This is why yoga practitioners who practice consistently for years develop not just muscular flexibility, but a fundamentally different tissue quality in their connective tissue. And why the stiffness that accumulates from years of sedentary work does not respond to occasional stretching sessions. The tissue is not being asked to change frequently or persistently enough to trigger the cellular machinery of remodeling. The fibroblasts are not receiving a sustained enough signal to alter their collagen synthesis patterns. The architecture remains as it is, and the body remains stuck in the positions its fascia has learned to enforce. The broader insight from the biology of fascia is about the nature of the body as a system. The classical anatomical model treats the body as a collection of discrete structures, muscles that attach to bones via tendons, joints that allow movement between bones, organs that perform specific functions in isolation from each other. The fascial network challenges this model fundamentally. Because fascia is continuous, a restriction anywhere in the network creates tension that is transmitted and compensated throughout the entire system. The plantar fascia of the foot is mechanically continuous with the calf fascia, which is continuous with the hamstring fascia, which is continuous with the thoracolumbar fascia of the lower back, which is continuous with the fascia of the upper back and neck. A restriction in the plantar fascia does not stay in the foot. It alters the tension throughout the posterior kinetic chain and can manifest as symptoms in the knee, the hip, the lower back, or even the neck. The body compensates globally for local restrictions, and those compensations create their own patterns of chronic load and their own fascial adaptations over time. This is why treating the site of pain is often insufficient for resolving chronic musculoskeletal conditions. The pain in your lower back may be the expression of a fascial restriction that originated in your hips or your hamstrings or your diaphragm or your feet. The symptom is where the system has run out of compensation capacity. The restriction is often elsewhere in the continuous network. Treatment that addresses only the symptomatic location is addressing the endpoint of a chain of compensations rather than the origin of the mechanical dysfunction. The fascia remembers every position you have ever held. It remembers the years at the desk, the hours behind the wheel, the habitual sleep position, the dominant hand you favor, the sport you played for 20 years and stopped, the injury you had at 30 that healed but never quite went back to normal. All of it is encoded in the collagen architecture, in the cross-link density, in the fiber orientation, in the water content of the ground substance of a tissue that was considered irrelevant for most of the history of medicine. The body you inhabit right now is the sum of that mechanical history, written in the most durable biological material your body produces. Collagen. The stuff that does not change quickly, does not change easily, but does change with a right input, applied consistently over time. That is the biology of fascial memory, not mystical, not metaphorical, molecular, structural. Applied biology in every position you have ever held, encoded in the tissue that holds you together, and understanding it is the first step toward changing it. There is one more layer to the story of fascia that connects its biology to something most people have directly experienced but never had a framework to understand. It involves the phenomenon of referred pain, and it involves a network of fascial trigger points that are among the most common and most misunderstood sources of chronic pain in the human body. A myofascial trigger point is a hypersensitive nodule within a taut band of muscle and fascial tissue that, when compressed, produces local pain, and often a referred pain pattern at a distance from the site of compression. If you have ever pressed into a tight spot in your neck and felt pain shoot into your head, or pressed into your hip flexor and felt an ache radiate down your thigh, you have experienced a myofascial trigger point. These points are not imaginary, and they are not simply tight muscles. They represent regions where the fascial tissue has developed a localized area of abnormal mechanical tension. Associated changes in the local biochemical environment, including elevated concentrations of inflammatory mediators and sensitization of the nociceptors in the surrounding fascial layers. The referred pain pattern of trigger points, the fact that compression of a point in one location produces pain at a predictably different location, is a consequence of the continuity of the fascial network and the convergence of sensory input from different body regions onto the same spinal cord segments. The brain, receiving nociceptive signals from a compressed fascial region, misattributes the source of the pain based on the patterns of sensory convergence it expects, producing the sensation of pain at a location that is sometimes far from the actual mechanical disturbance. This is why headaches frequently originate in trigger points in the neck and upper trapezius. Why knee pain is often referred from trigger points in the vastus lateralis or the iliotibial band. Why lower back pain is frequently maintained by trigger points in the gluteal muscles and the quadratus lumborum. The symptom is the referred pain. The source is the fascial trigger point, and treatments directed only at the symptom location, without addressing the fascial mechanics that created and maintain the trigger point, tend to produce temporary relief followed by recurrence. The reason trigger points develop in the first place is exactly the same mechanism we have been discussing throughout this video. Sustained mechanical load in a specific pattern, fibroblast response, collagen remodeling, and the progressive development of local fascial stiffness and reduced tissue hydration. A muscle and its fascial envelope that are chronically loaded in a shortened position develop trigger points preferentially at the musculotendinous junction and in the belly of the muscle, where the mechanical stress concentration is highest. A muscle that is chronically overlengthened, like the muscles of the posterior neck, in people with forward head posture, develops trigger points from the sustained eccentric load and the resulting fascial thickening in the posterior cervical fascial layers. Resolution of trigger points requires addressing the fascial mechanics that created them. Sustained pressure applied to a trigger point, the technique used in trigger point therapy and in many forms of manual therapy, works partly through the thixotropic mechanism we discussed earlier, transiently reducing the viscosity of the local ground substance and allowing the tissue to release. But sustained improvement requires changing the mechanical loading pattern that created the trigger point in the first place. Without that change, the fibroblasts in the region continue to receive the same mechanotransductive signals, continue depositing collagen in the same pattern, and the trigger point reestablishes itself over days to weeks. This is the fundamental challenge of chronic musculoskeletal pain management. The pain is real, the tissue changes are real. But the tissue changes are downstream of a mechanical loading pattern that is itself downstream of habitual posture, habitual movement, and habitual use. Treating the tissue without addressing the pattern is treating the effect without addressing the cause. The fascia will continue to remember whatever positions and movements you give it to remember. The most effective interventions for chronic fascial dysfunction work on multiple timescales simultaneously. In the short term, manual therapy, heat, and movement reduce viscosity, improve fluid dynamics in the tissue, and temporarily decrease nociceptor sensitization, providing symptomatic relief and creating a window of reduced pain in which new movement patterns can be practiced. In the medium term, sustained stretching and loading in new ranges of motion provides the mechanotransductive signal that begins shifting fibroblast behavior toward depositing collagen in new orientations. In the long term, consistent practice of the new movement patterns over months and years provides the sustained mechanical environment that drives actual structural remodeling of the collagen architecture, gradually shifting the tissue's mechanical memory toward the new position. There is no shortcut in this timeline. The tissue changes on the schedule of collagen biology, not on the schedule of your desire to be out of pain. But the timeline is not indefinite. Fascia is not a fixed record. It is an ongoing record that is being written and overwritten continuously by the mechanical inputs you give it. The same plasticity that allowed years of desk work to shorten and stiffen the anterior fascial chains of your upper body can, with consistent and appropriate mechanical input, allow those same tissues to lengthen, hydrate, and reorganize. The record can be rewritten. It just takes time, the right kind of load, and the understanding that you are working with a biological remodeling process, operating at the speed of collagen turnover, not the speed of thought. Your fascia remembers every position you have ever held, but it is also listening to every position you hold right now, every sustained stretch, every loaded movement through a full range, every hour you spend, not in the same compressed, chronically loaded configuration, is a new input to the fibroblasts, a new mechanotransductive signal, a small increment of remodeling in the direction of the position you are choosing to practice. The past is encoded in your tissue, but the tissue is alive, responsive, and continuously rewriting itself in response to what you do today. That is applied biology, in the connective tissue that holds you together, remembering your history and recording your choices, one collagen fiber at a time. Let me give you the final piece of this picture, the one that changes how you think about movement itself, not just pain and posture, but the fundamental mechanics of how a body moves through space. When you move, your muscles generate force. That is the part everyone knows. Muscles contract, pull on tendons, move bones around joints. But there is a second force transmission system in the body that operates in parallel with the muscular system, and that accounts for a significant portion of the total force transmitted during movement, particularly during high-load activities like running, jumping, and lifting. That system is the fascial network, and its role in force transmission was systematically underestimated until researchers began measuring it directly. The key structure in understanding fascial force transmission is the concept of tensegrity. Tensegrity is an architectural principle coined by the designer Buckminster Fuller that describes structures where integrity is maintained through a continuous network of tension elements balanced against discontinuous compression elements. In a tensegrity structure, no single element bears the full compressive load of the structure. Instead, loads are distributed throughout the entire tensile network, and the structure as a whole is stiffened and stabilized by the tension in the network, not by the compressive strength of any individual element. A geodesic dome is a macroscopic example. Your body is a biological one. The bones of your skeleton are the discontinuous compression elements of the body's tensegrity structure. The fascial network, including the tendons, ligaments, and fascial sheets that connect and surround every musculoskeletal structure, is the continuous tensile network. When you move, force is not simply transmitted from muscle to tendon to bone in a simple linear chain. It is distributed through the entire fascial network, simultaneously engaging structures across multiple body segments. The thoracolumbar fascia of the lower back, for example, receives tension from the latissimus dorsi on one side and the gluteus maximus on the opposite side during the rotation involved in walking and running. The two muscles never directly touch, but through the fascial network, they form a functional force transmission pathway that stabilizes the lumbar spine and pelvis during locomotion. Remove the fascial connection, and the muscles become mechanically isolated. The system loses its integrated force transmission capacity. This understanding of fascial force transmission reframes the concept of functional anatomy. Muscles do not work in isolation. They work in fascial chains, connected through the continuous tensile network to other muscles and structures that are anatomically distant but mechanically linked. Thomas Myers, in his foundational work on what he called anatomy trains, mapped the major myofascial meridians of the body, the specific chains of muscle and fascia that transmit force along consistent anatomical pathways. The superficial back line runs from the plantar fascia of the foot up through the calf, the hamstrings, the thoracolumbar fascia, the erector spinae, over the skull to the forehead. A restriction anywhere in this line alters the mechanical behavior of the entire line. A tight plantar fascia does not just cause heel pain. It increases tension throughout the entire posterior chain and can contribute to hamstring tightness, lower back compression, and cervicogenic headaches. This myofascial chain model explains clinical observations that the isolated muscle model cannot. Why treating the hamstrings does not resolve lower back pain that originates in hamstring tension. Why lower back pain treatment that includes plantar fascia, release, and calf stretching is more effective than treatment focused solely on the lumbar region. Why shoulder dysfunction is frequently linked to hip mobility restrictions through the lateral and spiral fascial lines. The body compensates globally. The fascia transmits the compensations globally. The symptom appears where the accumulated tension has reached its threshold. The practical implication is that effective movement and rehabilitation strategies need to work with the fascial chains rather than against them. Loading movements that engage whole myofascial chains, like deadlifts, swings, carries, and the movement patterns of traditional athletic training, provide mechanotransductive signals to the entire chain simultaneously, promoting coordinated fascial remodeling across multiple body segments. Isolated single-joint exercises, while useful for targeted muscle development, do not provide the distributed mechanical input that fascial chains require for optimal remodeling and function. The body that moves in integrated whole chain patterns, that loads the fascial network through its full range in multiple planes and directions, is providing its fascia with the most comprehensive remodeling signal available. The body that lives in a chair, moves in only the sagittal plane, and exercises exclusively on machines that isolate single muscles, is providing its fascia with the most restricted and pattern-reinforcing mechanical input possible. Your fascia is recording every movement you make and every position you hold, not as a passive victim of your habits, but as an active participant in your biomechanics, continuously remodeling to serve whatever demands you place on it. Give it the demands of integrated, varied, full-range movement, and it will remodel toward greater mobility, greater resilience, and greater capacity for force transmission. Give it the demands of repetitive, restricted movement and static postures, and it will remodel toward restriction, stiffness, and chronic pain. The choice, made thousands of times per day in every movement decision you make, is written directly into your connective tissue. That is what your fascia is, not packing material, not bubble wrap. The body's structural memory system, its force transmission network, its largest sensory organ, and its most honest record of how you have lived in your body. Applied biology, in the white tissue that anatomists used to throw away, now finally understood and waiting to be worked with.